Hi. In the last couple of weeks, we've explored acids and we've seen the importance of orders of magnitude in understanding acids. We're now going to start placing our knowledge of acids within the context of a larger chemical theory, and that larger chemical theory is Bronsted-Lowry acid-base theory. So up to now, our reactions have been in the form HA, the general acid, is reacting with water to make A minus plus H3O plus. But now what we're going to do is we'll still have, again, the general acid, HA. This is the acid. But rather than OS reacting with water, it's going to react with a base. The acid OS gives up a proton to become A minus. The base OS gains a proton to become HB plus. And A minus and HB plus have a name in the Bronsted-Lowry theory. A minus is the conjugate base, and HB plus is the conjugate acid. And we'll explore a specific example. The example we're going to look at, so here we'll put the base on this side. So that's the base. And we're going to switch over to the acid on this side, and the acid that we're going to look at is actually going to be water. So B is the base, it gains a proton to become HB plus. That's the conjugate acid. And the water was the acid, it loses the proton to become OH minus. And common bases that we would deal with are, for example, NH3, which is ammonia. Another common one we could deal with is C6H5NH2, which is aniline. And there are also ions, CH3, CO2 minus. That's the acetate ion. These are all common bases, and they can all interact with water. And they make the conjugate acids HB plus. And let's explore conjugate acids. So we're going to look now at this HB plus. It is an acid, so we're going to treat it as an acid here. And we're going to react it with water. And when it reacts with water, HB plus is the acid. It loses the proton to become the conjugate. This is the conjugate base because it's lost the H plus, and the water being the base here is gained, and H plus become HO3 plus. And what we can see is base is B, HB plus is the conjugate acid, HB plus is the acid, B is the conjugate base. The key is that B and HB plus are always conjugates of each other. So they're stuck together, and we're going to explore that next. Let's look at their equilibrium constants. So for the first reaction, we have K. We're going to define Kb versus a Ka, because this is the B is the base reaction, Kb of the base B, and it's going to be defined to be the products HB plus times OH minus divided by the reactant B, and that contrasts to the Kas that we know well. The Ka here, the acid is HB plus, and its products are B times H3O plus, that's the other product, divided by its reactant, HB plus. And it'll be very helpful to have some nomenclature, and the nomenclature that we're going to introduce is pKb is going to be minus log base 10 of kb, in the same way that pKa was minus log base 10 of Ka. So we're going to use those two relations. And so now let's do some math. What we're going to do is take kb of the base b, and multiply it by the Ka of its conjugate, Hb plus. And we'll plug in the expressions on top, and we're going to get, for Kb of the base b, Hb plus times OH minus divided by b, and for the Ka of Hb plus, we're going to get, copying from on top, b H3O plus divided by Hb plus. And we see something very nice. There's lots of cancellation. There's an Hb plus in the numerator, an Hb plus in the denominator. There's a b in the denominator, a b in the numerator. And so this whole thing simplifies to just OH minus times H3O plus. And I hope you can, you've seen this last week. OH minus times H3O plus, we have a name for that. That's Kw. And it's equal to 1.0 times 10 to the minus 14. And the very last thing we're going to do is take the log. We're going to turn these into pKa's. So minus log base 10 of Kb b, times Ka Hb plus, that's this expression, is equal to minus log base 10 of 1.0 times 10 to the minus 14. And please pause the video and see what you can do with this equation. It's a very nice result. Good. So this is a multiplication, and logs turns multiplications into addition. So this becomes minus log base 10 Kb b plus minus log base 10 Ka Hb plus, and this is minus log of this is just 14 minus, so, and minus log Kbb is just pKb of b plus pKa of its conjugate, Hb plus, and that is OS equal to 14. The pKa of an acid plus the pKb of its conjugate is equal to 14. And that's true for all conjugates. And we will use this result in tomorrow's class.